So here's another little exercise that's dealing with Gauss's law. And you can see in the problem definition, we're giving a equation for the displacement current here. It's y in the y direction. And so they want us to find the charge in a volume of a web-shaped box. And they define that here. So the key to this problem really is just making sure you get it set up correctly. So let's take a look at what this would look like then. So here's our web-shaped box. And so the first thing we want to notice here is we have the plane x equals 0. X equals 0. So in this drawing here, that's going to be this plane here. X is equal to 0 everywhere in that plane. We also have the plane y equals to 0. Y equals to 0. So that would be this plane here. Right there. Next we have z equals to 0. So for z equals to 0, that's going to be this bottom plane here. It goes right there. We're also going to have y equals to 1. Y equals to 1. So y equals to 1 is this triangle here. And then finally, we have this x plus z equals to 1. So that's this top plane here. And so I can try to draw that if that's helpful. So that's this plane here going there. All right, so there's our web-shaped box. So it's a totally enclosed volume. And so they're asking us to determine what the charge is inside of this volume if we have a displacement current defined in the y direction. So since we have this AY term here, anything that is perpendicular to the y-axis is going to be 0 by definition, because the dot product will be 0. So that means that the only planes that will have any impact to this at all are going to be the y planes. And so that's this plane and this plane here, the two triangle planes. Now, when we look at our equation, it's y equal AY. Well, on this plane here, y is equal to 0, so that's going to make our d term equal to 0 everywhere. So the only thing that's left then, again, let me highlight this, is going to be this triangle here in red. Everything else is 0. All the other planes are perpendicular to y, and then this plane here, y is equal to 0, so we just need to integrate over this plane here. So we recall from Gauss's law that the total charge, the total charge can be defined as the integral over a surface of the displacement current vector dotted with the surface vector. It's over the entire surface. So again, we've determined that it's a 0 for all of the sides except for that one side of this triangle. And so that triangle is defined by our x. So here's our x going from 0 to 1. And then it's defined by this dimension here, which is the x plus z plane. So if we solve this equation here for z, then z is going to be equal to 1 minus x. So that being the case, let's rewrite this then. We're going to have two dimensions that we're integrating across. The first one's going to be from x equals 0 to 1. And then the other one is going to be from z equal 0 to 1 minus x. And that's going to be integrating on that plane, y is equal to 1. So our d term then is just 1 a y hat, which is the unit vector. That's going to be dotted with dx, dz are two variables of integration, and they are perpendicular to a hat y. So this dotted with this is going to equal to 1. So your a hat dotted with a hat is equal to 1. So now we can just perform this integral. It's just a simple calculus problem now. And so we could rewrite this just to make things simpler. It's just going to be x equals 0 to 1, integral z equals 0 to 1 minus x of dx dz. And when we perform the inside integral of z, that's going to give us integral from 0 to 1 of 1 minus x, because we've integrated over the z term, dx. And so when we integrate that, we're going to get 1/2. So again, just a calculus problem. 1/2, and that's going to be coulombs. So the total amount of charge that would be present inside this volume that would give us a current density defined as this is going to be 1/2 coulomb.